Good morning, I'm Mr. Precella with my Math 1325 class, and we're looking at the generalized power rule and chain rule for differentiating. And let's recall what we had said yesterday. We said that if you wanted to differentiate some function of x raised to a power. Up until now, all we could differentiate was just variable to a power, not a quantity raised to a power. If you have some function of x, some quantity raised to a power, that's where we use the generalized power rule. The generalized power rule says that you differentiate the outer function first. We know how to differentiate a power. That plain old power rule says you bring down the exponent and you subtract 1 to get the new exponent. But then, because this is more than just a single letter to a power, you then have to multiply by the derivative of that inside stuff. You differentiate the outer function first. That's the power function. We know to differentiate the power function, you bring down the exponent, you subtract 1 to get the new exponent. But then you have to multiply by the derivative of the inside function, which I'm denoting with f prime of x. And this is just a specific case of the chain rule. The chain rule says that if you have, the chain rule says if you're looking at a composition of functions, say you have f of g of x, that you want to differentiate. You're differentiating a composition. You differentiate the outer function, leaving the inside function alone. You then have to multiply by the derivative of the inside function. Now that's what the generalized power rule is doing. You're differentiating the outer function, that power function, leaving the inside function alone, and then you multiply by the derivative of the inside function. I want to start, I have a couple of examples I want to do. And first one, this is number 6. And let me rewrite that, it's so light. F of x is equal to 8 times the square root of 6x squared plus 9. From here on in, the rest of the semester, whenever you see a function written with a radical, what are you going to have to do?
Change the radical to a negative exponent.
It's going to be a fractional exponent, but you're right about it being an exponent, okay? It'd be negative if it were in the denominator, but it isn't. But it'll be a fractional exponent. The square root of 6x squared plus 9 is the same thing as 6x squared plus 9 to the 1/2 power. And now we're ready to differentiate. I'll do the differentiation in red. F prime of x is equal to, you differentiate the outer function first, that power function. What do you do with the 1/2? Times it by 8. So you have 8 times 1/2. The inside stays as it is, 6x squared plus 9. What do we do to get the new exponent? Subtract 1, so you have a 1/2 minus 1. But then you have to multiply by the derivative of the inside stuff, 6x squared plus 9. That doesn't look like a plus, does it, there? And 8 times 1/2, we know that that's 4. You have 6x squared plus 9. What's the new exponent? 1/2 minus 1, 1/2 minus 2/2. There you're getting that negative 1/2. But we need to multiply all of this by what? What's the derivative of 6x squared plus 9? 12x. And we have a monomial times a monomial. 4 times 12x, that's a 48x. We still have that 6x squared plus 9. And that's a negative 1/2. And my math lab would take that. Typing that in. And now, if this were a multiple choice problem, they may not have that as an answer. In which case, let's convert it back. Let's first of all change the negative 1/2 to a positive 1/2 exponent. But keep in mind, my math lab would take that red box, and if it's not multiple choice, then that's perfectly fine as a final answer. So first of all, change the negative exponent so that it's positive. You put the 48x on top, and on the bottom you have 6x squared plus 9 to the positive 1/2. The factor that has a negative exponent is moved down to the denominator and it becomes a positive exponent. And now what can we do to get rid of that exponent of 1/2? Same thing that we did here. We took that square root and we wrote it as an exponent of 1/2. Now we're going to go backwards, writing it as 48x on top and a square root of 6x squared plus 9 on the bottom. Any questions? If you're differentiating something other than just a single letter to a power, anything other than just a single letter to a power, that's where you use the generalized power rule. You differentiate the outer function, that power function, and we know how to differentiate exponents. We bring it down, subtract 1, but the inside stays as it is. But then you have to multiply by the derivative of that inside stay. Let's do another one. This is like number 10 in your homework. So let's see. Same instructions. We want to find the derivative. Find the derivative. I'm going to make that a little darker. Y equals 1 I had someone call my office. It was sort of strange. The phone rang this morning. It never rings. And here was the question. Are we having class today? Because it's a holiday weekend. Valentine's Day is 2 days from today. Are we having... You gotta laugh, okay? You gotta laugh. Yeah, yes.
Sorry about that phone call.
That was someone in the 8 o'clock class. The bad thing is I need to look at the roll sheet. I don't think she was there. I don't think she came. Oh, goodness. Oh, I tried. This is a quotient, but if I have just a single number as a numerator or a denominator, I try to avoid the quotient rule. I think I can rewrite this function without, so I don't have to use the quotient rule. I'm going to pick the 4x plus 7 to the 6th power up. I'll move it up there to the numerator, so we'll just have 1 times 4x plus 7 to the negative 6. So I rewrote it using a negative exponent, and now I think this will be It'll be less painful than using the quotient rule, at least. Y prime is equal to. What do you do with the negative 6? Bring it down multiplying, okay? So 4x plus 7 stays as it is. The inside doesn't change. What power will we have now? Negative 6 minus 1 is a negative 7. Then what do? Take the derivative of the inside. What's the derivative of 4x plus 7? Just a plain 4. That's nice. And once again, we have a monomial times a monomial, so that we can multiply the negative 6 times 4. That's a negative 24 times 4x plus 7 to the negative 7. And that's perfectly fine as a final answer, but let's suppose we wanted to rewrite it without a negative exponent. Suppose we want to rewrite that, but without a negative exponent. We would say, okay, we have a negative 24 on top. There's no negative exponent on that negative 24, so negative 24 is going to stay where it is. We move the 4x plus 7 down, and that negative 7 exponent becomes a positive 7. Either one of those would be acceptable. Any questions there? And I have a couple of word problems also. This is like your numbers 8 and 9. Any questions before we go on? Okay. And here we have it. Let me move it up some. This is like y'all's number 8. The cost of producing X bags of dog food is given by C of X equals 900 plus the square root of blah blah, where X is bounded between 0 and 5,000 inclusive. Find the marginal cost function. This function only works for X values between 0 and 5,000, and that's fine. They want us to find the marginal cost function. Marginal means we're going to do what? Find the derivative, okay. And at first glance, that function there looks awful, but it's really not that bad. I think I'm going to recopy it, though. I'm going to copy it a little bit larger. So here's my cost function. There's my cost function. And I should have done this when I was recopying it. What should I have done? I'm feeling lazy today. There's something I shouldn't have even written it the way it's written there. What should I have done? Write it using, get rid of that radical, write it using an exponent of 1/2. And that's the thing I'm going to differentiate. C prime of X. I'll see people getting a 450 at this point, but no. That is not 900 times the square root. Notice this isn't 900 with the parentheses immediately following it. There's a plus there. So we differentiate the 900, and then we differentiate this quantity here. When you differentiate that 900, what are you going to get? 0. The derivative of a number by itself is just 0. So people incorrectly think of that as 900 times the square root. No, that's the sum. So we differentiate each term individually. Now, the derivative of 900 became a 0. We have to differentiate this parenthetical expression here. It looks like it's a quantity raised to a power. So what do? Okay, so you bring down that 1/2, you're multiplying. The inside stays as it is. Do we have an exponent up here? Negative 1/2, 1/2 minus 1. You're subtracting 1. 1/2 minus 2/2 gives you a negative 1/2. Is that finished? No, we now have to multiply by the derivative of that inside stuff. So now we're going to multiply by the derivative of 600 plus 35x squared minus x. The derivative of 600 is 0. The derivative of 35x squared is 70x, okay. The derivative of minus x is, okay. That stuff there came about by differentiating the parenthetical expression. You differentiated that. And, well, I guess what can we do? We have I think I'll just write it as 1/2 times 70x minus 1. I'll say it's a 1/2 times the binomial 70x minus 1. And then you still have that 600 plus 35x squared minus x raised to the negative 1/2 power. So we're going up. 600 plus 35x squared minus x raised to the negative 1/2 power. And my math lab would take that. Now, if you view an example for this problem, I'm pretty sure that they don't stop there, okay? But my math lab will take it in this form here. I think they go on and say, okay, they're going to change that negative exponent so that it's positive. That 70x minus 1, it doesn't have a negative exponent, so it's going to go up on top. 1 times 70x minus 1, that's on top. On the bottom, you have a 2. And you have that trinomial raised to the negative 1/2. That's going to become the trinomial raised to the positive 1/2. And what do you think they do then? What do you think they do then? They make that 1/2 exponent into a square root. Two square roots of 600 plus 35x squared minus x. Any questions there? Now, if you're typing this into my math lab, they would take either of these 3 boxed in answers. Oh, not 3 boxed in. I only have 1 boxed in. But it would take this one. It would also take this one here. Any questions there? Once again, this is number 8 from your homework. Number 8 from your homework. Any questions? Okay. One more. This is number 9. An amount of $11,000 is deposited in an account with an interest rate of R% per year compounded monthly. At the end of 8 years, the balance in the account is given by, and they give us this little formula. Find the rate of change of A with respect to R written as a percentage for the interest rates given in parts A, B, and C. The rate of change, what does that mean? What are we going to have to do to find the rate of change? Find the derivative. And they've given us this function. The funny thing is, I just finished discussing compound interest in Math 1324, and this is not the same formula that we use in Math 1324. Notice for that rate per period, you normally take the little rate as a decimal and divide it by the number of periods. What they've done is they've multiplied above and below by 100. So when we get down here to A, B, and C, you don't have to convert the 1.2 to 0.012. You just plug in 1.2, 2.4, and 4.2. So, but for our purposes, we have to find the derivative. So let me recopy the problem. Here's the function. Oh, and that rate of change, that's the thing that says find the derivative. So we have the function A equals 11,000 times 1 plus R over 1200 to the 96th power and we're going to start differentiating. Oh, once we've found the derivative, we'll have to plug in 1.2, 2.4, and 4.2 for R, but the real work here is finding that derivative. So here we go. A prime equals. Notice we have a quantity raised to a power. That's what says use the generalized power rule. So you take that quantity, 96, times 11,000. The inside stays as it is. 1 plus R over 1200. What's the new exponent? 95. 96 minus 1 is 95. Are we finished with the derivative?
No.
Say no. No, we're not. We need to differentiate what? We have to now differentiate that inside stuff. And that's a 1 plus. Oh, and by the way, remember, when I have a variable just divided by a number, I think of it as a number times that variable. That's like a 1/1200th times R. So here's what I'm thinking. It's 1/1200th times R.
Why is the 1 still there?
Why is the 1 still there? We haven't differentiated this. Are you saying right here? I'm just saying now we need to differentiate this stuff. I have not differentiated it yet. Oh, 96 times 11,000. What does that turn out to be? I have a calculator. We have 96 times 11,000. I'm getting a 1,056,096. Yeah, okay. So that's a 105, 6 and 3 zeros multiplying. So that 1 plus R over 1200 to the 95th. Now let's differentiate. What is this derivative going to give me? Differentiating, what are we getting here? Just 1 over 1200. The derivative of 1 is 0. The derivative of 1/1200th R is just 1 over 1200. We have two constant monomial factors. We can multiply the 1,556,000 by the 1/1200th. So that's going to be dividing. What are y'all getting there? I'm getting an 880. Someone check me. 96 times 11,000 divided by 12,000. Yes? So we still have the 1 plus R over 1200 raised to the 95th power, and that's my A prime. 96 times 11,000. Then I had to multiply that by that 1/1200th, which is just dividing by 1200, to give me a final answer, a final coefficient of 880. Agree or disagree? Yes, I agree. I double checked myself. So, and we're not through with the problem. What do we need to do now? Plug in the numbers. Plug in 1.2, 2.4, and 4.2. So now plug in 1.2 to give us a prime equals 880 times 1 plus 1.2 over 1200 to the 95th power. Part B, and we'll have to punch that into our calculator in a moment. Part B, they want us to plug in a 2.4. And notice I'm not converting that 2.4% to 0.024. The way they've modified this formula up here, we're using R. The way they're giving it as a percent. So they're actually making it easier for us. We'll punch that in a moment. And what's the last interest rate? 4.2%. So A, B, one more, C. 4.2 over 1200 to the 95th power. And I'm going to let y'all punch that in your calculator yourself, okay? So these are all the examples I wanted to do today over the generalized power rules. So I think I'll stop recording now, okay? So bye-bye.